first.
Recording in progress.
Okay, again, good morning and welcome to the Thursday session. You probably came to be accustomed to the style that we have been doing. Namely, Tuesday, we introduce the key concepts for the chapter. And then Thursday, we continue to finish those topics and do some applications, some problems from the book. Today, I have 3 problems for you guys that we're going to go thoroughly on. And those problems are, of course, you're required to go through the numbers and double check them. That's part of the discussion item. In addition, for this special week, there was an item from Tuesday where you were supposed to put the first law in your own words, okay? So that is basically what we need to be posting starting from today on this discussion. So there will be 3 problems. Some of them probably are going to go in detail. And even though I go in detail, I would still recommend that you guys go back through them to double check the numbers. Because like I said before, I make mistakes. So you would want to catch those and also to learn from them. You have to do them because, as I was saying repeatedly, anything we do in class in terms of problem sessions, any homework assignment, you are responsible for, because content in the exams will be basically picked up from these discussions that we have them. So that is why they are important and you have to do them, in addition to the fact that you're going to be graded on them for participation. So this is in general, so I'm hoping that you guys get to the work habits of what we're doing. And then on Thursday, we still have the labs that we have to do. So we discuss the labs and that's basically the process we've been doing so far. An important item, and I know that another one of you showed up, another item of great importance is the lab that is due this weekend. This is the first lab, basically the lab 1 is due this weekend. You are strongly urged, and I know there are a couple of people who did not submit it yet, to submit it before the due date. I will grade it immediately thereafter. If you don't submit it by then, you're going to receive a 0 mark on it. Okay, that is number 1. Number 2, I will grade it with the understanding, because this is the first assignment in terms of labs, to be a little bit lenient in the grading. But if you don't receive full credit on any given section of the lab, and the rubric is out there, so you can see exactly how much you're supposed to get on that section or that item. And if you don't receive full mark, you're going to receive a comment in there. I strongly urge you to take those comments seriously, because down the road, the grading will be a little bit more, if you should say, more in line with the rubric. So if you don't receive full mark, and if you receive comments from me, take those seriously. And the first assignment is going to be graded immediately after it's due, so that you'll have ample of time to make corrections as time goes by. So you will, because you have a lot of labs, with the understanding that you can make up for this grade easily. Unless you're planning to get a C in the class, then probably you can do whatever you want to. But I strongly urge you that you guys work, because the labs are worth 25%. So that will knock off 25% of your grade, and you really don't want that. So you want to take that seriously, and you would want to, in the next lab, to make the corrections. For example, if you forgot to put your name, you're going to lose points. If you did not do the abstract correctly, you're going to lose points. If you did not answer the questions with a full sentence and also missed units in them, you're going to lose points. If you did not do the data, all of them as they're supposed to be on the table, you're going to lose points. And the rubric tells you how much you're going to get and how much you're going to miss. And the graphs also have to be properly labeled, the x-axis, the y-axis, the labels, the units, whatever there is, a trend line, if there is we're asking for a trend line, slope if we're asking for a slope, and things like that. So you're going to also lose points according to the rubrics. And then at the end, the conclusion also has a minimum requirements of sentences and also structure. In other words, it's looking for a data analysis. It's looking for numbers in the conclusion where you refer to your findings and how much errors you think there is and how can you correct that if in case it needs to be corrected. So in other words, there is a structure and there is a rubric that we're going to follow. And starting from this weekend, when the lab is after it's due, I'm going to go and grade them. And as I was saying, because you're not used to the way that I do things, I'm going to be a little bit lenient for this first assignment, and I will give you comments on every one of them, provided and hopefully that you will take care of them in the next labs because they are still not due, okay? And if you did already do it, you can make corrections and you can go and fix what needs to be fixed. Sounds good?
Yes, sounds good.
Very good. So let's continue the topic we started last week. So let me share. Last week, was it last week? No, it was 2 days ago. Sounds like a long time ago. So let me share with you my notes. And when I say that, I really urge you guys that you take notes as we go along. Don't rely on the screens and things like that, because the more notes you take, the more you're going to really be accustomed to these concepts. So let me go to the main points to review what we have discovered from chapter 19. So basically, the first thing was the first law, which I wrote it this way, Q plus W, with the understanding that Q is the heat associated with added to the system, and work is W is the work done on the system. So this is added heat, and this is work done on the system. Now, I said, and before that, this statement is actually algebraic, meaning I could have heat added negative, which means I remove heat, okay? That's what the sign means in this case. Or I could do negative work on the system. In other words, I could have the system do work. So basically, that's what the word algebraic means in here, that this thing, delta U, can be positive or negative at the end of the day, okay? In other words, the internal energy of the system, this is what it is, internal energy, could go either up or down or stay the same, okay? In an ideal gas, that's a special case actually of all of these things. The energy, the change in energy is simply equal to NCV delta T all the time, always, no matter what, okay? Where CV depends on the nature of the gas. If it's a monoatomic gas, it's 3/2 of an R. If it's a diatomic gas, it's 5/2 of an R. If it's a polyatomic gas, it's around oh no, that's gamma, that is 1.3. Basically, you can find it, okay? If gamma, which we defined as the ratio of the molar specific heat at constant pressure divided by the molar specific heat at constant volume, this number is 1.67, or roughly about what? 7 divided by, no, it's 5 divided by 3, okay? And then the other one is 1.4, which is exactly 7/5. Or finally, around 1.3, okay? So when I say 1.3, it's not exactly 1.3 for all polyatomic gases. So the first one is mono, like helium. The second one is diatomic gases, like diatomic molecules, like, for example, nitrogen. And the last one is, for example, H2O, okay? That's a polyatomic, as long as the gas now, the water now is in the gas form, which is above 100 degrees Celsius. So this is gamma. From gamma, you can find basically what CV is. Remember, CP is, or CP is equal to CV plus R. That's another relationship that we found last time too. And this is true all the time, no matter what, always. Okay, so gamma, which is CV plus R, over CV. In other words, this is 1 plus R over CV. I can solve this equation for R over CV and find it to be gamma minus 1. In other words, CV is simply equal to R divided by gamma minus 1. So if you give me gamma to being 1.3, I can tell you what CV is. It's going to be, for a polyatomic gas, basically R over 0.3, and so on and so forth, okay? So CV is always, you can find it, okay? If you know the gas. If you don't know it, then if you don't know the nature of your gas, then in this case, once you find CV, then you're in business. Then you can tell what the gas is, or at least what type of configuration the gas is, okay? Because if it turns out to be diatomic, it may not necessarily be nitrogen. It could be oxygen or any other diatomic gas in here. And if it's 1.67, it may not be necessarily helium. As a matter of fact, helium has to exist. I mean, it's very rare to find it. You have to really work very hard to do it. It could very well be neon, for example, or argon, or any other inert gas in here, okay? So that's basically, but you know its nature, okay? That's the point in here. So this is some of the stuff that we have found. So this is delta U always. Now, the work usually is around Q and W. W, there is a formula for at the end that I wrote to be minus the integral from whatever state you start with to the end state you're at of PDV, okay? So that's basically the formula. In the book, they write positive in here, but if they write positive, they better fix this number in here and make it negative, that's all. But this is really the common way of doing business, okay? So I'm going to go through several examples today, and I'm going to pinpoint this issue in here so that you have clear understanding of exactly what that means, okay? In other words, if you decide to put a plus in here, delta U then becomes Q minus W. So there is always a minus one way or the other. So in other words, you could skip this W letter at all and write delta U from now on to be just Q minus the integral of PDV. So in this case, it's the same always, no matter what. Either if you define the work as being the integral from PDV, then there is a minus in the formula. Or you work to define the work with a minus itself, the whole thing becomes W, then there is a plus in there, and that takes care of business, okay? So that is really the way that we define this way, this thing. Obviously, there is a kind of an issue with Q, the heat, and the Q from this formula, you can write it as basically Q is equal to delta U minus W. That's one way of finding it too, okay? That's how much heat is added. Obviously, if it turns out to be negative, it was extracted, not added, okay? So this is what we have seen. We have seen also some interesting cases in here, namely 4 processes. The first one is an isothermal process. An isothermal process, that means the temperature doesn't change, stays the same no matter what. This has an immediate implication that the energy does not change. Period. So a system that goes through an isothermal process will not see its energy change, meaning that the work and the heat must satisfy this relationship so that if I add them, I get 0. It turns out the work in here, if I remember correctly, was a positive, no, it was a negative NR T, because T is not changing, so it doesn't matter which T you put in there, it's the same T for this process, ln of V final over V initial. And this is positive if this ratio of these volumes is less than 1, because the ln becomes negative, and then the negative times negative will become positive. Or it's negative if in case the final volume is greater than the initial volume. In other words, in an expansion, W is negative. Because in an expansion, the final volume is greater than the initial volume. So this is more than 1, and ln of more than 1 is positive. So the end is going to be negative. In a compression, what I mean by compression in this case is a shrinking. So if in case the volume shrinks, obviously the final volume is less than the initial volume, and this ratio is less than 1. And ln of a number that is less than 1 is negative times negative becomes positive. So the work is positive in this case. So that takes care of this state in here, okay, business. It follows immediately in an expansion that Q is positive actually, because of this expression, that in this case, Q is actually positive, and in this case, Q is negative, okay? So that when I add them up, they end up to be 0 because the energy has to better stay 0. So this takes care of everything that we need to know about this process, okay? So that's it. The other process that we identified also was kind of easy also is an isovolumetric process or an isochoric process. And this is by definition, delta V doesn't change. The volume doesn't change. From here, immediately we know the work is 0 because of this expression. If the volume doesn't change, then the final volume is equal to the initial volume. The end, no matter what, dV is 0. So the finite element, the infinitesimal work is dW is 0. And you sum 0 from on a bounded integral, you're going to get 0 because the final value and the initial value are the same. So it's going to be 0 no matter what. Okay. So the work is 0, which means that delta U, which is, I remind you, is NCV delta T, is Q, because there is no W in here. If there is an increase in temperature, if the temperature goes up, then delta U is positive and so is Q. That means I added really heat to the system in such a way that its energy increased. If delta T is negative, that means the temperature went down. That means I removed heat Q and delta U went down. That's it. That's all, takes care of everything now. So this process is more or less also easy. The third process that we identified was an isobaric process. And this one, delta P is equal to 0. I can't say much about it other than the fact that the pressure is the same. Well, the work turned out to be easy in this case. It's minus P. Which P you're talking about? It doesn't matter. It's the same. The initial pressure, the intermediate pressure, the final pressure, they're all the same because P is the constant. Then the integral of a constant is going to be the final minus initial. And this takes care of everything in here. So that's the work. Okay? That is the work in this situation. Okay? I could write it, plug in the P back in, and plug in the P back in, and this will become pressure times volume, and that is according to PV equal to nRT. N is the same, R is the same, and the volume changes to final volume. The pressure is the same, so it's going to be minus nR, which is going to be common for these two terms, times the final temperature minus the initial temperature. So I can write it as minus nR Tf minus Ti. Again, if Tf is greater than Ti or Vf is greater than Vi, W is going to be negative. And vice versa. Okay? So that is the work. The heat needed some work, but at the end of the day, we wrote it as Cp times delta T. So this is delta T actually. So N times Tf minus Ti, where Cp is the molar specific heat at constant pressure. Similar to the molar specific heat at constant volume. As a matter of fact, the work, the energy, which I always say, it's NCV delta T. Here is where we define gamma and where we define all kinds of things. And we found a very useful relationship, always true. Cp is Cv plus R. Okay. The final process that we identified and required a little bit of calculus for us to get its properties is an adiabatic, sometimes, not sometimes, always actually, referred to as an isentropic process. And we will see why that is the case, okay? So this is because the entropy doesn't change. So we're going to talk about the entropy later on. But for right now, Q is 0. There is no heat added or subtracted, okay? That's basically what adiabatic process stands for. Then in this case, it's easy. Delta U is equal to W. This is NCV delta T. The difficulty with this process is everybody changes. P is changing, V is changing, and T is changing, okay? Everybody's going every which way. So we needed a way to find how P and T are related to one another, because if I find how P and T are related to one another, I can always find this relationship and find the missing link. If I can find how P and T are changing, then I can find the volume later on using this relationship. If I find how P and V are changing, then I can use this relationship to find the T. If I can find how V and T are related, then I can use this relationship to find the P. So that's basically what this thing is. It turns out there are at least 2 common expressions that are commonly used, and there is a third one that is less used, but you can use it too if you want to, that the P times V to the power gamma is constant, okay? Where gamma is that ratio of the molar specific heat, Cp over Cv, by definition, okay? Or alternatively, or the same, okay? So they're identical. To say TV to the power gamma minus 1 is another constant not related to this one, okay? So there is an NR between them. This constant and that constant, they have an NR between them. For one thing, the dimensions are not correct. That's how you can catch that these constants are not the same. This has a units of a Pascal, and a Pascal is a force divided by an area. That's what the pressure is. And a force is a kilogram times meter per second squared. That's what a force is, divided by an area, which is meter squared. Cancel that by that. So the Pascal itself is simply a kilogram divided by a meter second squared. That's what the Pascal is in SI. Times the volume to the power gamma. And a volume is a cubic meter. So this expression in here is somehow a kilogram divided by meter times second squared times a meter to the power 3 gamma. So I can write this one as a kilogram meter to the power 3 gamma minus 1, the whole thing 3 gamma minus 1 because I have it in the denominator, divided by second squared. So this is the units of this constant. The units of this guy is completely different. So this is a Kelvin times again a cubic meter to the power gamma minus 1. So this constant is a Kelvin meter to the power 3 gamma minus 3. So this is a completely different constant, has completely different units. So they are not the same constant. So when I write them constant, as a matter of fact, they have to do with a point in here. In the PV diagram, we're concerned only with this expression. But this will become handy in some cases. Okay. So this is in a nutshell what we did last Tuesday. Does this review help a little? Yes, maybe.
Yes, it does.
Yeah.
Yeah, at least so that we can touch base of what we did to bring them a little bit closer. I know you did stuff in chemistry, but probably the perspective was completely different than what you're doing right now in physics. So there is another relationship I mentioned it briefly, but that relates P and T, okay? And it's a little bit convoluted, a little bit involving gamma and the exponents and things like that. Take any of these two. If you're trying to get to write PT out of this one, use this expression to eliminate V off of it. V is clearly nRT over P, and plug in into this expression, and you'll have that expression P and T, how they are related. Or use this expression and get rid of V also in favor of P and T, and plug in here, and you're going to get that relationship that you're looking for. Okay. There is an alternative way of deriving this PV to the power gamma, and it's a little longer than what we did last time. Last time we took this expression right away, and we took it in this form, in the infinitesimal form. Okay, that is actually what the work is, and this is what the energy is, because there is no heat in this case. So, and we played around with this expression where P is equal to nRT over V, and we basically moved things around and we integrated and we found that constant. And at the end of the day, we found basically this expression, TV to the power gamma minus 1. And from using the ideal gas law, we found PV to the power gamma. There is another way of doing it, but it's a little longer, and you can find this expression PV to the power gamma. It doesn't matter how you arrive to it. The point in here is this expression is a useful one. I remember, at least from last semester, and I usually include the old videos in the recordings for you guys. And I think in one of those videos, you will find the longer way of finding it, and it's the same way. Okay, same thing. So let's plug all of this on a nice PV diagram, see what we're talking about in here. So this is P, and this is V. Oh, let's keep it on the same screen in here. Obviously, the pressure can never be negative, so this cannot be true. And the volume can never be negative. So the only thing that is of interest to us in these functions are the first quadrant, because the pressure is always positive and the volume is always positive. Typically, I mean, in typical problems, you will find volume is actually in liters, okay? The pressure is an atmospheric pressure. So if that's the case, you have to be very careful with your units, because 1 liter is 1 cubic meter divided by 1,000, okay? And also 1 atmospheric pressure is 101,000 pascals. So if you're going to use the joules again, and if you're going to use the value of R, which is 8.134 joules per Kelvin per mole, you better be careful, okay, with the units, because this guy is in joules. And if this is in atmospheric pressure and this is in liters, you have to keep these two conversions in mind, okay? Combined, if I write P times V, well, P, if it's given to me in atmospheric pressure, it's already 101,000 pascals. And if the volume, so if this is in ATM basically, times a liter, then the volume is 1,000th of whatever it was given to me. So those 3 zeros and these 3 zeros, they cancel. So this number is 101 of whatever it is, okay? So it's 101 in joules, okay, to get it back in joules. So in other words, you have to be careful with your units, because typical problems, they use liters and they use atmospheric pressure, because are those daily numbers that we deal with. It's much easier to say 2 liters of something than to say 0.002 of cubic meters, okay? Or centimeter cubes or something like that. So you have to be careful with this unit business, okay? So that is one thing. Now, let me try to get some colors in here going. Let's start with the isothermals. So this is an isothermal at T1. In other words, this entire curve is P, which is the independent variable, the dependent variable, is equal to a constant nRT1 over V, and V is your independent variable. It drops when V goes to 0, this blows up, this goes to infinity. When V goes to infinity, the pressure drops to 0. But for another temperature, it could be like this. So this is for T2, which is clearly less than T1, okay? So this is another isothermal of P equals to nR T2. T2 never changes on this line. It's the same thing. divided by V. So this is isothermal. And this is another isothermal at two different temperatures, okay? The higher the temperature, the higher the curve on the PV diagram. The lower the temperature, the lower it is on the PV diagram. That answers that question. Okay. Let's take this point on this isothermal of a volume, which I'm going to call V1, of a pressure, which I'm going to call P1. So this point has definite values for both the pressure, the volume, the temperature being T1, and whatever you want to define on it. If I take another point on this isothermal, okay, this point, let's call it V3 for right now, okay? It has a pressure. If I know the volume, then I know the pressure. P3 is simply equal to nRT1. It's the same temperature divided by V3, okay? And the process going from this point to this point is an isothermal process. This is the one that has all of that W and that has all of that Q, and delta U is 0. Going from here to here, delta U is 0. Okay. On this volume, V1, on the second isothermal, I have a different pressure, P2. Now this P2 satisfies this equation. P2 is equal to nRT2 over V1. Okay. This is a different isothermal. It has different temperature, T2. So the process going from here to here is actually what we were talking about earlier as an isochoric process. This process is an isochoric process. The volume does not change. So this is where W is equal to 0. There is no work in here. Okay? There is no work in here associated with this process. In a vertical line like this one is an isochoric process. So there is no work. The volume is V1 in this point, and it's V1 in this point. The pressure has dropped from P1 to P2. The temperature has dropped from T1 to T2. But that's basically what it is. That's this process. Now let me draw another process in here, and that is this process. The pressure doesn't change. It's P3 here, and it's P3 here. As a matter of fact, it's P3 everywhere in here. But the temperature has changed from this isothermal, which is another equation actually that I can find in here. This is another isothermal. If you're curious trying to find this temperature, which I'm going to call T3 quickly, T3 satisfies this pressure, P3, times this volume, V1, divided by NR. So that is that temperature. Clearly, that temperature is less than T1, but more than T2 from the graph. So that is another isothermal. T3 is another isothermal. So the temperature T3 here, the temperature is T3 everywhere in here. And it has increased from T3 to T1. If I go this way, of course, provided I'm increasing in the volume from V1 to V2, to V3, I'm sorry. Okay, so this is what I meant with all of these processes in this description. So we have our isothermal, here it is. We have our isochoric in here, and we have isobaric in here, all three of them. So where is the last one? The isochoric, the adiabatic process or isentropic process. If I take this curve, it's going to cut sharply in here, okay? And this curve is defined by P v to the power gamma is constant. You're asking what is that constant? Since it passes by this point, that is P1 times V1 to the power gamma. And how much gamma is? It's Cp over Cv, depending on the nature of the gas that we're talking about. And if I want to find it here, what is this volume? Well, this volume must satisfy T2 because there is passes by this temperature. T2 times this V2 in here, this volume in here, to the power gamma minus 1 equals to this T1, this temperature T1, times this volume V1 to the power gamma minus 1. So I can find this temperature T2, this volume V2, because I know what T1 is. It's this temperature, this isothermal. I know what T2 is. It's the second isothermal that I'm interested in. And I know what V1 is. It's this point. So I can find V2. Do you guys agree that V2 is calculable from this expression?
Yes, it is.
Everything is in there, so we should be able to get it. Now, the last thing that probably interests me is this pressure. That probably I should give it a different name than P2. So it's going to be P2 prime. P2 prime is equal to, clearly from this isothermal, NR T2 divided by this volume that I just found, V2. So everything I need to know about this one. So the expression for this curve now is this function, PV to the power gamma. In other words, the function that I'm looking at is P equals to P1 V1 to the power gamma minus 1. That is a constant. This is a number. This is a fixed number divided by V to the power gamma. V is your independent variable. V is your X value, if you wish, on this graph, and P is your Y value in here. So this is a function I need to plot, okay? This is the discontinuous line that I drew in here. That is the adiabatic line. This is the adiabat, okay? So we have all of these processes on the PV diagram properly represented, okay? This is where the units matter a lot. When you have nonlinear expressions like this one, with the conversion factors become a problem. Here, it's 101 easily joules. But what in the world the unit for this guy? Remember gamma in here. So this is where it's safer to proceed in SI. Okay, so the units really matter in here. Otherwise, you're going to get calculations for a pressure that don't make sense. If you leave the atmospheric pressure and all of the other factors, there is a factor of 101 to some power in here, or something in here that mess up your calculations in here. So it's safer to proceed in SI all the way through, okay? So even though the PV diagram is given to you in L and atmospheric pressure, hopefully you're going to take care of that. Obviously, if you look at this graph right now and you just joined and you zoom straight through to here, you have no idea what we're talking about. And you saw it build up from scratch all the way to this complexity. So you really have to go step by step on it to understand how each and every one of these processes are. Makes sense graphically? Everybody?
Yes, it does.
Okay, anybody else? Everybody else? Yes, no, maybe?
Yeah, it does.
Okay, very good. So let's take some examples. And for that, I'm going to get the book open. And I urge that you guys have the book with you guys. I have 3 problems, as I said before. Problem 23 from page, let me share the screen first. Share. Oh, let me change the color back to normal color. So it's problem 23 from page 636. And two problems for the next page, 38 and 39. Okay, so if you have the book ready for you, go guys, get them going and get your pen and paper, and let's do these problems step by step, okay? And if you have any questions, please stop me right away and let's get that clarified right there and there. We don't want any ambiguity. We don't want any kind of magic that somehow works only in this problem and does not work somewhere else. And then you will have another problem that is slightly different or even different than this one, and you have no idea how to proceed. That is not good, okay? So that is really the plan in here from doing these problem sessions, is to give you a little bit more confidence and more experience in how to do these problems. So it says, problem 23, an experimenter adds 970 joules of heat. So it says Q is equal to positive. That's what adds means. 970 joules of heat. So Q is equal to positive 970 joules to 1.75 mole. So N is equal to 1.7. That's the number of moles, okay? Of an ideal gas, so when they say an ideal gas, I know PV equal to nRT. Okay? To heat it from 10 degrees Celsius to 25 degrees Celsius. So TI is equal to 10 degrees Celsius and TF is equal to 25 degrees Celsius. Do I need to convert to Kelvin yet? Hold on, okay? If it involves delta T, then you don't need to do that because you're going to add 273 from here and you add 273 from to the other one and you subtract to 2. So at the end, that's a wasted exercise because then you didn't really need to convert. Now, if you end up with a ratio of these two temperatures or you're calculating PV equal to nRT, then you better convert, okay? So that is one thing I didn't mention about this graphs in here. All of these temperatures in all of these expressions are in Kelvin. They're not in degrees Celsius. So in this problem, they gave us in degrees Celsius, and I might be tempted to convert, but I would say, hold on for a second. Don't do the conversions yet, okay? At constant pressure. So this heat was added at constant pressure. So we are in this curve. We're here on this green line, was added to this system in here. Are we going this way or are we going that way? That depends. Are we reducing the volume or increasing the volume? That depends. Clearly, in order for the heat to be added, the temperature has to go up. So let's see if that's the case or not. Okay, let's see what happened to delta U. That will tell us what's going on. The gas does, okay, here is where the issue might be. This is what there is kind of a contradiction, okay? It says the gas does, that's why I really wanted this problem for you guys to look at. This is what they say, okay? The gas does. For me, when they say does, the work better be negative. Why? Because how does it do work if it's positive? That means it has to give part of its energy, and that part of its energy better be negative. But they tell you does a positive 230 of joules, okay? This is in compliance with their convention. This is so that when you write delta U, the reason why they say that, so that when you write delta U, you're writing it as Q minus W. So if this is indeed the way that you wrote it, then this makes sense. But if I write it the way that I understand it, W is actually negative 230 joules. That's how it does work. It loses energy of that amount. So at the end, I'm going to write it as Q plus W. Algebraically, it's going to be the same thing, whether you do it this way or whether you do it this way. Do you guys agree about the algebra? So this is the book. This is how everybody is. Do you guys agree that the algebra is going to boil to the same thing? Whether, was somebody going to say something?
Yeah, so just to be sure, you see, the reason we're saying it's negative is because it's specifically using the word does, right?
Yeah, because they say it does work.
Mhm.
And in this case, how does it do work? It better loses energy. That's how I understand it.
Mm,
That's
okay.
how everybody in thermodynamics book understand it. Since it does work, that means it lost energy in the form of work of this amount, which is 230 joules.
Okay.
And lost is negative.
Mhm.
Okay. But the book is insisting on this convention here for delta U, which is Q minus W. Then it's taking it positive, so that at the end of the day, delta U is going to be the same thing. Okay? So that's why I brought this example, honestly. It's all about this one. The rest is really, the rest is, how do they say, academic. So it's really work during the expansion. Another key word that it has to be negative, it's an expansion. Okay? So it's expanding. As it expands, it does work on the environment. So it better loses energy from within, okay, in the form of work. Calculate, that's the part that is probably relevant for some of you. Calculate the change in internal energy of the gas. Basically calculate delta U. If you take the first convention, if you take the book approach, let's do the book way. Delta U is equal to Q minus W. Q is, what is it, 970. I wrote it up there. It's 970 minus positive 230, and you can do the math. 70 minus 30 is what, 40? 9 minus 2, that's 700, and it's a positive value of energy. Make sense? The proper way is to actually say that delta U is equal to Q plus W. And in this case, it's going to be 970 plus the energy that is lost in the form of work, which is negative 230. And that's going to amount to the same value, positive value. Did I make a mistake in the algebra? I don't know. If I did, hopefully you guys corrected. But the point being in here, the two should be the same answer. Sounds good?
Yep, sounds good.
Okay, so now calculate the internal energy, the change in the, and now calculate gamma. They didn't give us gamma. Well, we know for one thing that this delta U is equal to NCV delta T. Okay. Look what they gave us. They gave us N. They gave us CV. Oh, they didn't give us CV. They didn't. We need to find it. But they gave us delta T. This is why the conversion is not important now, because all we need is to subtract 10 from 25. So the delta T is actually equal to 15 degrees Celsius, because that's what 25 minus 10 degrees Celsius is. And it's the same thing, it's 15 Kelvin. It's the same amount. Because if you wish, add 273 to this number and add 273 to this number, this becomes 298, and this becomes 283. And when you subtract the two, you're going to find 15 Kelvin. So that exercise is a wasted time. So there is no need for it. And that is because we're dealing with delta T only. We don't care about anything else, okay? When we have delta T, delta U, so we have this number also. So all we need to do is find CV. Once we find CV, we can find gamma. Because remember, R over CV is simply equal to gamma minus 1. In other words, gamma is equal to 1 plus R over CV. So if we find CV from this expression, we can find it. That's one way of doing it. The other way of doing it is actually, since we know Q is equal to, in this case, because it's at constant pressure, it's NCP delta T. We have Q, which is 970. So this number is given. So by the way, we found this one 740. This one is actually 970. We have N, the number of moles, 1.75 moles. We have also delta T, which is the same thing, 15 Kelvin. And we can find CP from here. If we find CP, we can actually find gamma also. Because remember, let's multiply this expression by CP. Okay, let's write it down. So CP over CV is equal to gamma. That's how we defined it. And CP, trying to think of a way of doing this algebra quickly in here without really having to do it. So multiply by CP and you divide by CP, okay? So, so we can write gamma equals to 1 plus R gamma times divided by CP. So that's another way of finding it, okay? If I can find, so move everything to the other side, so gamma times 1 minus R over CP equals to 1. So this gives me gamma in terms of CP as just being 1 over 1 minus R over CP. In other words, if I find CP from this expression, I can use this expression to find gamma also. You guys agree that there are two ways of finding gamma?
Yeah, I agree.
Okay. Does everybody follow also? Everybody else or not so far? Yes, no, maybe? If you're not clear, okay, good. If you guys are not clear, please talk now. I know that I have about 20 of you, slightly less than that, but only a couple who are participating at this point. So I assume everybody else is clear for them. Otherwise,
No, yeah, I got it.
Okay, very good. This is the time when to ask these questions, okay? So there are two ways of doing business in here. In other words, finding CV from this expression, because we have delta U, we have N, we have delta T. Finding CP from this expression, we have Q, we have N, we have delta T, we can find CP. We can use actually this 2 and at the end find gamma, simply equal to CP over CV. That's it, okay? As a matter of fact, we can write these two expressions as, okay, one by one. We have Q equal to N CP delta T, and we have delta U equals to N CV times delta T. Take the ratio of these two expressions side by side. Now the delta T doesn't matter, it cancels. The N doesn't matter, it cancels. And this gives me gamma equals to the ratio of Q over delta U. Actually, this is a lot smarter than the other two methods. It does not require much algebra at all. So this is 970 divided by 740, okay? So this is so easy that probably is going to give us the answer right away. Okay, let's check the algebra quickly in here. Can anybody check this number in here? Mathematics is probably, no, let's do Wolfram. Mathematics, probably will need it for some graphing down the road, so it's better to get it going. So, just enter the thing, 970 divided by 740. It's giving me 1.31. Did you guys find it to be 1.31?
Yeah, that's what I got as well.
Yeah.
So this is a polyatomic gas. What did they say? Did they say the nature of this gas? They did not. Calculate the gamma for the gas. They didn't ask you even what type was it. But we know it's polyatomic because it's not 1.4 and it's not 1.67. It's around 1.3. Sounds good?
Sounds good.
Okay. You guys probably need to do the other two to also to verify that they're correct, okay? So we need to check that if I find CV, plug in this expression, which gives me, so let me clarify the other two quickly. So I can find delta U from this expression NCV delta T, and that's why they gave us delta T actually, is to be able to calculate the CV business. So we'll find CV from this expression, which is delta U, which is 740, divided by N, which is 1.7, divided by delta T. That gives me CV. Once I find CV, I can use the expression of gamma equals to 1 plus R over CV. And R is equal to 8.314 in SI units, okay? Joule divided by Kelvin by mole, okay? And CV, you can calculate it from this expression also. So that is one way of finding gamma. That's a second way, actually, of finding gamma. The third way of finding gamma is to use the expression for Q equals to NCP delta T, and use this expression to find CP. And CP from here is going to be Q, which is 970, divided by the number of moles, which is 1.7, divided by delta T, which is 15 Kelvin. And from here, once we find this expression, we're going to use that expression for gamma. That is 1 over 1 minus CR over CP. 1 over 1 minus R over CP. Is this sound correct? Because CP is usually greater than R by amount CV. So this number is less than 1 when you invert it. And 1 minus less than 1 is going to be a positive number. So we're good, okay? So we should be able to find gamma from here. Again, use the same value of R once you find CP. And it should be around 1.3 if this calculation is correct. So this is part of the discussion. The thing is to finish this problem using different ways of finding gamma. Okay? And that gives you a way to check actually on yourself. If you find gamma to be 1.7, for example, or if you find gamma to be 1.1, then you know something went south. You know something is not correct in here. Okay? You know, if it was an experiment, maybe we made tremendous errors. Instead of finding 1.67, we got it into 1.73, for example. Or instead of getting it 1.3, we got it 1.38, for example, or 1.25, for example. So that's reasonable in an experiment, but not in calculations like this one. Okay. So we understand this problem hopefully thoroughly. The biggest reason why I brought it up is because of this issue of the positive and the negative, so that you guys have a handle over that. Okay, let's look at the other two examples. And they are problems 38 and 39. Okay, so in problem 38, it has a nice picture for us. Let's draw it. The volume is in cubic meter, so we're good. The pressure is in Pascal, actually. Okay, it's in Pascal times 100,000. Okay, so whatever those numbers are, you have to basically multiply them by 100,000. Okay, that's what those things are. So we have a point A, we have a point B, and we have a point C. Okay, from point A to point B, we go this way, and from point B to point C, we go this way. This is A, this is B, and this is C. And from C to A, or from A to C, we go this way. Okay, so this is clearly a clockwise direction through which we're going through this one. So if I calculate W in here, I know it's going to be negative without doing anything. They tell you that this process in the PV diagram, N is equal to 3.5. So N is 3.25. So this is the number of moles, okay, of an ideal helium gas. So gamma is equal to 1.67. Is equal to, what is it, 5/3. So we know that, okay? They're asking me for CV. CV is equal to 3/2 of an R, and Cp is equal to 5/2 of an R. This is what helium is. It's a monoatomic gas. Okay. So there is some information that is implied. The minute you look at it, you know exactly what you're dealing with. Okay. You know a lot of things about this gas just by the. You know a lot about the problem just by reading what the problem is saying. Part Ca of this process is isothermal. So this is an isothermal. This is clearly an isobaric. And this is clearly an isochoric. Okay, so 3 of the 4 processes are already here in this, this problem. They give us the volume at point C, which is 0.4. 0.04, I should say. They give us the pressure, which is 200,000 Pascal. 2 times 10 to the power 5 Pascal. They gave us also the volume at point A, which is a fourth of this volume, 0.01, and that is a cubic meter. Okay. Find the pressure of the volume of the helium at point A. So we need to find PA, this pressure. Okay, it's clearly more than 2 atmospheric pressure. So if you're doing 200,000 Pascal, if you find the answer to be 100,000 Pascal, you know you did something wrong from the picture at least. Okay. So let's see if we can find it. Since this is an isothermal, I really need to find the temperature T first. Okay. Once I find the temperature T, I can use PV equal to nRT and I'm in business. But if I look at the problem in here, part B, find the temperature of helium at points A, B, and C. So it's asking for the same temperature at points A and B. So there is, A and C. So probably it's not asking for that technique to do this problem. So let's look at this problem. The pressure at point C times the volume at point C satisfies this equation. The pressure at point A times the pressure at, this is the temperature at point C, by the way, satisfies the ideal gas law too at point A. But the temperature at point A and the temperature at point C are the same because this is an isochoric process. I mean, isothermal process. So these 2 temperatures must be the same. So all I have to do is take this equation and divide it by that equation. On the other side, I'm going to find 1 because the temperatures are the same. So here gives me PC times VC over PA times VA, I should say in here, times VA, and that should give me 1. From here, I can solve for PA, which is equal to PC times VC over VA. And I already have the answer. Well, the pressure PC is 2 times 10 to the power 5 in pascals. The volume in here is 0.04 cubic meter. The volume in the other location is 0.01 cubic meters. The cubic meter cancels the cubic meter, and I'm left with a Pascal, as it should be. So PA, this is 4/1 times 2, that is 8 times 10 to the power 5 Pascals. In other words, this number is 8. Is it believable that 8 is more than 2? Obviously, yes. So I can assume that probably I didn't do mistakes in my calculations. So this is part A of the problem. Part B of the problem is to find the temperatures in points A, in points B, and in point C. Well, we just saw that the temperature in point A and point C are the same. And I can use any of these equations to find it. So TA is the same as TC is equal to any of this equation, PAVA over NR or PCVC over NR. It's the same thing. If I use the point C, then PC is 2 times 10 to the power 5 times VC, and VC is 0.04 cubic meters, divided by N, which is 3.25, times R, which is 8.314. The answer is going to be in Kelvin. okay? Because everything is in SI. Sounds doable? Let me, for the sake of this problem only, because I really need to find those two temperatures. Let me stop sharing. And let me move this calculator to this side so that you can see what I'm doing. And let me share with you the calculator, which is Mathematica, actually. It's a big calculator for this task. So this is going to be 2. I'm going to leave 10 to the power 5 alone because, no, I need it. I'm sorry. I thought I'm calculating pressures. So times 10 to the power 5 times 0.04 divided by, open parentheses, 3.25 times 8.314. This sounds like it's a big number. Oops. It's 296 Kelvin. I mean, it's room temperature, really, because 296 minus 273, that puts it at 23 degrees Celsius, which is exactly how it feels right now. Right now is about 23 degrees, maybe slightly warmer than right now, but that's exactly how much the temperature is. So it's room temperature. So I'm curious about TB now. TB, let's find TB. Well, we have PB, which is equal to PA. And we have VC, which is equal to, VB, which is equal to VC. So from the graph, it's clearly VC is equal to VB, 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 I'm sorry. There is no D in this graph at all. And PA is equal to PB. So that means we have PB times VB is equal to nRTB. And we use this expression to find what this temperature is. So TB is going to be, of course, PB, which is 8 times this thing, times VB, and VB is 0.04, which is equal to VC, actually.
Professor, we don't see OneNote.
Oh, I'm sorry. Stop sharing. Share. Thank you for. You guys see it now?
Yes, we can.
Yes.
VC is VB from the graph. VC and VB are the same. And PB and PA are the same. Okay. So the pressure in point B is the same pressure at point A. So the pressure in point B is the same pressure at point A, and the volume in point B is the same volume as point C. So if I use this expression PB/VB equal to nRTB, from here I'm going to find what this pressure is, okay, what this temperature is. So technically, according to this expression, this gives me TB to be just P at that point times the volume at that point divided by nR. Well, I know what the pressure is. It's exactly PA. I know what the volume is. It's exactly VC divided by nR. If I use this expression, then TB is going to be 8 times 10 to the power 5. That's what this pressure is, pascals, times VC. VC is 0.04 cubic meters divided by the number of moles, which is 3.25, times R, which is 8.314, equals to, look at this term that we found at 296 Kelvin. It's the same number as this one, with the exception of instead of 2, I have 8 in here. That's all. Everything is the same. So all I have to do is multiply this number by 4, and I'm in business. So it's 4 times 300. It's almost 1200 Kelvin. So that's basically my point in here. 296 times 4. It's about 1184 Kelvin. So it's 1184 Kelvin. Okay. I took advantage of this fact that we already did this calculation in here, where all the numbers match. The only thing that changes is the pressure. So the pressure is 4 times as much as before. So the answer is about 300 Kelvin. This should be about 1200 Kelvin. Okay. So we found that temperature. It's important to find these temperatures because it looks like we were on this isothermal, which is about 296 Kelvin. We are now on another isothermal that is 1184 Kelvin. So that is really what this graph is saying, okay? So we did part B. Part C, how much heat entered or left the helium during segments A, B, B, C, and CA. So we want to know how much heat did it go in it, okay. From part A to B, so we're doing C now. From part A to B, Q is equal to NCP delta T. Q is equal to 3.25 times CP. CP, remember, this is a monoatomic gas, so this is 5/2 times R times delta T. Delta T is 1184 minus 296. So in going from this temperature of 296 to this temperature of 1184. And this process is at constant pressure. This is an isobaric process. I mean, isobaric process, I should say. So that's how much heat it went there. So you can calculate now. You have R, which is 8.314, and you can do the numbers. So you can finish this. Okay. For the part B to A, B to C, I'm sorry. Well, this is an isochoric process, and going from B to C. From B to C, this is an isochoric process. So Q is going to be NCV delta T. Well, N is 3.25 times CV is 3/2R. And you know what R is. It's 8.314 in SI. Times the final temperature, which is 296, excuse me, minus 1184. Clearly, this is going to be positive. This is heat added. Okay, this is clearly is going to be negative. So this is extracted. Okay. And you guys understand that this is doable? Although this number is going to be higher than this number because you have a 5/2. So in other words, whatever you find in here, all you have to do is divide it by 5 and multiply it by 3. So you really don't need to do all of this algebra all over again and change the sign. The final value is from C to A. For that, we have found it to be equal to positive nRT times ln of V final over V initial. That's what we have found it. So if I do this calculation, because this is an isothermal process, so this will be Q is N, which is 3.25 times 8.314 times the temperature. Temperature is 296. This is this process at this constant temperature, 296. It's not changing. Okay. I need to do one thing quickly in here. If you guys don't mind, I'm going to lock the car. So, personal thing. Can I take a break quickly in here?
Yeah, no problem.
Yeah, because I received a notification from from the car that it's unlocked. Sorry about that. Okay, done. Okay. So the point being in here is the ln of the final volume is 0.01 divided by 0.04. Those are the ratio of the two volumes. The volume shrunk from going from C to A. Obviously, this number is going to be negative. Why is it going to be negative? It's because this ratio of ln of 1/4 is negative, is actually equal to negative ln of 4. Okay? So you plug in the numbers now. So you need to finish this one too. Finish this and finish this. This one is going to be negative for sure. Okay? Does everybody follow so far so good? Yes, no, maybe?
Yes.
Everybody else?
Yeah.
Okay, very good. So we're in good business. So we have found the answer to part C. And after we finish this problem, we're going to do the next problem after we take a break, you know, the typical thing, because I think we still have about 5 minutes in this thing in here. In this lecture thing. So the last question is, how much did the internal energy of the helium change from A to B, from B to C, and from C to A? Obviously, from C to A is 0. From C to A, I know the answer to that. I don't have to even do anything in here. From C to A, delta U is equal to 0 here in this part. So when you're asked questions like this, you always have freebies. You always have free things that you can guess right away. You don't even have to do anything. So since they said to do from A to B, from B to C, and from C to A, I'm going to say this is equal to 0. Why? Because it's an isothermal process. The temperature didn't change, so delta U did not change. How much is it in here, though? Delta U is equal to NCV delta T. And how much is it in here? Delta U is equal to NCV delta T. The gas is the same. The CV is the same. And delta T is the same. Okay? With the exception that at some point it increased from 296, went from 296 to 1,184. And in the other case, it went down from 1,184 down to 296. So the CV is the same. The N is the same. The only thing that changed is the sign of that delta T, that's all. So if I find a number in here for delta U, all I have to do is put the negative of that number in here and I answer the second one too. So this is done, provided that I do this. And this is equal to 3.25 times CV, which is monoatomic gas, times delta T, which is 1,184 minus 296. Once I do this calculation, flip the sign, and I have done it in here. This is the trick with problems of thermodynamics. You really don't need to do all of them. You need to do one, maybe you can find the other, maybe, okay? And this one in this case is a free answer. So imagine this problem is part of an exam, and each of these two questions is worth 2 points, and you don't have time, you run out of time, and this is, you can do it. You can do it even before doing anything. You can just look at the question and say, hey, that is equal to 0. I don't have to do anything, okay? This is 0, so you'll get 2 points guaranteed in here. And then if you pay attention to what's going on with these expressions, you only have to do one work and then flip the sign in there, because these two expressions are identical, with the exception of the delta T changes sign, that's all, for these two processes. Make sense?
Yes.
Yep.
Finish this part, too. Indicate if it increased or decreased. Obviously, the first one has increased because the final temperature is higher than the initial one. So this is an increase. This is a decrease. For the same reason that the other one increased, this one decreased, because the final temperature is less than the initial temperature. And this does not change. Why? Because it's an isothermal. Temperature stayed the same. Okay. So we have done problem 38 to some extent, all of it, with the exceptions of the numbers. So I trust that you guys are going to finish the numbers. And when we meet after the break, which is going to be about 15 minutes. So right now it's around 9:25. So 15 minutes should put us around 9:40. Sounds good?
Yes, sounds good.
Okay, so I'm going to leave the session open. Please do not close your session. Just basically turn off your microphone if you have it on, or video or something. And we'll meet around 15 minutes from right now. So around 9:40, we will resume the class to do the remaining of the problem and also do the lab. Okay? If we were on campus, we would be actually moving between the room assigned down to the lab. So we're going to get the break to go and get something to drink and see back each other. Okay, so let me stop. First of all, the room. So basically the question was about the discussions. Like I said, try to stick to the instructions as much as you can. And if you have difficulty with it, I know some of you have been messaging me, emailing me, that's fine. I usually respond to your emails, and I even do the comments on the discussion items. Basically, if there is an issue, if not, basically you're good, then everything is fine. Okay. The purpose of those discussion items is really to make sure that you're fully engaged in the class and you're not basically, because what happened with the online classes was in the past is people say, okay, I'm taking an online class, I'm going to leave it to the last 2 weeks or the last 3 weeks, and I'm going to basically do everything together and submit it. And that's not going to work in this class. A calc-based course that is heavily loaded, and you guys probably have seen it already. Every week there is a ton of materials in terms of content, assignments, and things like that. And if you do that, you're going to risk it all. Okay, this is not the class for it. So it's for me a way to make sure that you guys are doing the things you're supposed to be doing on a regular basis, to make sure it doesn't overwhelm you at the end and basically you give up on it. Okay, sounds good.
Sounds good.
Okay, very good. So let's continue this problem stuff. So let me find it first and let me share with you. Okay. So the third problem that I promised we do today. So again, the discussion item today is really to go back into item 1 from Tuesday, which was to put it in your own words as far as the first law of thermodynamics. And the second one is to finish all of these calculations that we're doing today, okay? To make sure that all the numbers correct. And when you post something, okay, any number, don't forget the units. You will lose points for missing it, for no units, basically. This is a big deal, okay, in physics. And you will lose anywhere between 1 to 2 points, depending on the type of assignment, depending if it's an exam or not, you will lose points. So this is really something you really don't want to ignore, okay? So put the units at the end of the day. That's very important. So even when you post the discussion items, post them also with proper units. Don't tell me the velocity is 650, it doesn't mean anything. And I have already seen it, specifically for this point. So it has to be in meters per second or kilometers per hour or light years per, I don't know how many years, whatever that you're using, okay? It's like going to the grocery store and telling the lady, hey, I need 23. 23 of what? The store sells all kinds of things, okay? So, problem 39. So this problem also has the diagram that I'm going to draw, and it has a PV diagram also. So there's the volume. They didn't give me any units for it. There is a pressure, and they gave us points A, and point B, they give us this weird looking curve in here that is going from B down to A, okay? And they gave us point D, which seems to be immediately have the same volume at least as point B, but also has the same pressure as point A. So this looks like, and it's going this way, by the way, from A to D with this arrow. So this looks like it's an isobaric process. This looks like an isochoric process from D to A. And from point B and A, there is also another point in here, which is C. And again, the arrow is pointing from A to C. This is an isochoric process. This is also an isobaric process. And where the volume of C is the same volume of A, and the pressure of C is the same pressure of B. So this is basically what they gave us in the problem, at least from the picture. When a system is taken from point A to B, okay, so we're going actually from A to B first. Along path ACB. So along ACB, so this path, 90 joules of heat flows into the system. So Q is added to the system, 90 joules. That's how much we added heat to it. Okay, it flows into the system, so it was added to it. So its energy, it's increased by this much when we go through ACB. Into the system, and 60 joules of work is done by the system. So W is equal to, actually, according to the way that I do this thing, and according to thermodynamics, is negative 60 joules. If you believe the book will say it's actually positive 60 joules. Okay? But you have to remember which formula to use, that's all. Similar to problem 23. Okay? That's how much W is. So the question is, how much heat flows into the system along the path ADB if the work done by the system is 15 joules? So the question now, from ADB, which is the other one, the other path, and going from A to B. So the whole point is leaving A and ending up in B. This is what the story is. Now it says how much heat, so we don't know how much heat is here. If the work done by the system is 15 joules. So the work done by the system is 15 joules, according to the proper convention, according to the book, it should be a positive 15 joules. Okay. The question is there, how much Q is? Well, the change in energy is the same, regardless of which way you go, because the energy is a state variable. So there is an energy associated with the point A, and there is an energy associated with the point B, and delta U, which is UB minus UA, it doesn't matter how you get to it, whether you say UB minus UC plus UC minus UA, or you say UB minus UD plus UD minus UA. It's the same thing. This is going through the process ACB, which is this one. This is going through process ADB, which is the second one, because the energy is a state variable. So you're allowed to do this algebra. This is delta U, and this is delta U between the points AB, and this is between the points AB. Same thing. So it doesn't matter which path you take, the change in energy is the same. Why? Because the energy is a state variable. U is a state variable. It's actually called the state function because it depends on PV in this case, state variable. I mean, if anybody walks right now amongst us, I mean, somebody who has never heard of this first law of thermodynamics or any of this stuff, and he looks at this expression, I'm going to agree 100% with a little bit of knowledge of algebra. This is the same as this. Does it make sense to you guys?
Yes.
Yeah, all I did was subtract a number and add a number to it. That's it. It's like going from the first floor to the 7th floor, okay? So instead of taking the elevator from the first floor to the 7th floor, you decide, you know what, I'm going to take the elevator from the first floor to the 3rd floor and from the 3rd floor to the 7th floor. It's the same thing. That is exactly what's going on in this case. Somebody else, you know what, I don't like this. He said, okay, I'm going to go from the 1st floor to the 5th floor, and then from the 5th floor to the 7th floor. It's the same thing. So somebody else said, you know what, this thing is actually UB minus UD plus UD minus UA. It's the same thing for them. And that is the other route they took. Somebody else says, you know what, I'm going to go from the 1st floor to the 11th floor. And then from the 11th floor down to the 7th floor. It's the same thing. Okay. Somebody else might go all the way to probably somewhere in here. Okay, and come back to B. That's the same thing. It's the difference in energy that matters. Okay. So this is pure algebra, and it works only because it's state variable. For heat, it's not. You cannot tell me that the heat from here to here is always the heat from any other path. The heat is not a state variable. Work is not state variable. So this algebra works only because U is a state variable, and any state variable, this works for them. And this is actually the potential energy, the gravitational potential energy, because it's also a state variable. And so is the electrical potential energy too. That's the same stuff in here. Okay, so enough talk about that. So let's do this thing in here. Okay, so what we're saying then is delta U, which is in the first case, this is how much delta U is for AB. It's equal to
Q minus
Q
plus W.
According to us, it's plus W, or according to the book, it's minus W. So this is the process AECB. This is this formula, really. Or Q plus W for the process ADB, or according to the book, minus W, okay? We know what Q through ACB is. We know what W through ACB is. We know what W through ADB is. We don't know what Q is, and that is a question, actually. So from here, it's clear that Q from ADB, what's it been called, Q? Or let me read the question again. How much heat flows into the system along the path ADB? That's exactly what we're asking here. So Q through ADB is Q through ACB, I'm sorry, plus the way that we write it, A through ACB, or according to the book, minus W through ACB, minus this work. Yes, the work through ADB, or according to the book, plus the work ADB. It's going to be the same answer no matter which way you cut it, okay? It's going to be the same amount of heat. So QADB is going to be, this Q is easy. This Q is just this 90 joules. This W, according to us, it's actually a negative value of 60. According to the book, it's a positive value of 60, but you're going to subtract it. So in either case, you're going to put a negative 60 in here. Okay, so this 2, they boil down to negative 60. This one is minus W. According to us, it's a negative 15. So it's going to be a positive 15. According to the book, it's a positive value anyway. So when you move it, it's going to be with a positive sign. So it's going to be a positive 15 no matter how we cut it. Okay. So 90 plus 15, that's 105 minus 60. 105 minus 60. Is it 55 joules? Yes, maybe.
Yeah.
90 minus 45. Yeah, it sounds like, no, it's 45 joules. 45. Because 105 minus 60 is 45. 45 joules. Please check this thing in here for us. Check it.
30, yeah, 45, yeah.
45, okay. So this is how much heat was added to this. It's a positive number. So it's added. See the advantage of using this convention? So when you see a positive, you see added. When you see negative, you see a subtracted. End of the story, whether W or Q. But for the book, you have to flip it for W. If you see a positive, you say going to be removed. Okay. If you see a negative, you're going to say added. So it's backward for the book. Okay. But if you stick to the convention that we're doing for both W and Q, you're safe. If you see positive, you say added no matter what. Okay. If you see W and negative, you say subtracted from the energy of the system. End of the story. That's why the convention that is used in the thermodynamics books actually is better than the one that is used in this book. Okay. In either case, you have to be careful with this sign business in here. Otherwise, you should be in good shape. Okay. So we answered part A. Part B, when the system is returned from B to A along the curved path, the absolute value of the work done by the system is 35 joules. Okay. Here is what they're saying. When we go from B to A on that path, the curved path, W from B to A in absolute value is equal to 35 joules. They don't tell you if it's positive or negative. Again, we should be able to tell. It's a compression. So we must have done work on it. So this is, according to us, it should be positive. According to the book, they're going to put a negative there. Okay? Because the environment did work on it. Shrunk its volume from VB down to VA. Okay? Does the system absorb or liberate heat? No, the question has nothing to do with the work. It has to do with heat, Q. Okay. Well, we know delta U from A to B, which is equal to, either of these formulas would work for me. What is it? This one. Because I know Q and know W. So it's going to be 90 joules minus 60 joules. So it's actually 30 joules. That means if I go from A to B, the energy increases by 30 joules. Now, if I go from B to A, the energy decreases by 30 joules. You have to make the distinction. Since the path that they're talking about is actually going from B down to A, then that is actually decreased by 30 joules, not an increase by 30 joules. If I go from A to B, the temperature increases, so that's fine. That's an increase in the internal energy. But going from B to A, the temperature decreases actually, and that is the pressure is lower, the temperature, the volume is lower, therefore the temperature is lower, therefore the energy is lower. Okay, so in this case, we have gone down by 30 joules. So this is actually delta U from B to A is actually equal to negative 30 joules. So that is U. We know also the work now is positive. W is equal to positive 30 joules according to us. According to the book, it's actually negative 30 joules. Okay. That's how they write this thing for the book, because they write delta U to be Q minus what we write it plus W. In the book, it's minus W. It's going to be the same thing. So if you write it minus according to the book, times minus is going to be positive. If we write it positive the way we write it, times positive is going to be positive. So we know going from B to A that this is what's going on. Delta U BA, that this is equal to Q going from B to A in this path, plus W, and W is actually, we know it's 30 joules according to us. According to the book, it's minus W, okay? So from here gives me Q from B to A is equal to, so I should probably label this one as BA also, as BA in here, which is this 30, is it 30 joules? No, W is given to be, how much the, 35, I'm sorry. 35 W was given. That's what the question was saying, okay? So we have to pay attention to this number here. So Q is actually delta U in BA minus, according to us, delta, the work from B to A, and according to the book, it's gonna be, what is it? Plus WBA. Okay, it's gonna be the same number anyway. So QBA, according to us. We know delta U is a negative number, it's negative 30 joules. Minus W, and W, according to us, is positive number. According to the book, it's a negative number, but you add that negative number. So in either case, it's going to be minus 35. So this thing is going to be minus 65 joules. So we removed heat from the system of 65 joules and going from B to A, and that's understandable because the temperature went down. So we cooled it by doing work on it. That's how the compressor works in your AC unit or in your refrigerator. There is a compressor actually behind the scene that does work to compress the gas. And in doing so, that compressor actually will go later on and remove the heat from your stuff that is in the refrigerator. So that negative in here, in this expression, is true for both expressions, because the way we wrote it is W is positive because we're doing work against the gas. So we're adding energy in the form of work. That's why W for us is positive. And when you move it to the other side, it's going to be negative because that's how algebra works. Okay. For the book, they define delta U as Q minus W. And they say in this case, W is negative. So when you move it to the other side, the negative that was in the formula becomes positive, but W, they take it to be negative. So at the end, it's going to be the same thing, negative 30, negative 35. And the energy is negative. The energy went down because in going from A to B, it increased by 30 joules. So now better it decreased by 30 joules. Make sense so far? Yes.
Yes.
Okay. Anybody else? Confirmation from some other people?
Yep, makes sense to me.
Okay, very good. Assume that the rest of you are good. That's why you're not talking. But sometimes if you're bothered with something, this is the time when you speak up. Otherwise, it's going to be a problem down the road. Okay. So part C, if UA is equal to 0 and UD is equal to 8 joules. So remember, we've been dealing so far with difference in energies, but now they tell you take UA to be 0 and take UD to be 8 joules, okay? Find the heat absorbed from the process AD and DB. So from AD, how much heat is there? And from DB, how much heat is in there? So that's basically the two questions that we're supposed to answer, okay? Knowing this much energy. So we know from this expression here that delta U delta U, I should say, from A to D is simply equal to 8 joules. 8 minus 0 is 8, okay? That leaves us from delta U from, again, A to B, excuse me, equals to usually UB minus UA. And this we found it to be 30 joules from the previous calculations. This is exactly this number. Delta UB, delta UAB, that is 30 joules. But I write it as, in this case, as UB minus UD plus UD minus UA. Well, this is UA is 0, UD is 8. So this is 8 joules, because this is 0 and this is 8, okay? And this is 30 joules. So clearly, UB minus UD, delta U from B to D only, it's 30 minus 8, and that is 22 joules. If you look at this process carefully, from B to D, from D to B, I'm sorry, this is an isochoric process. The volume does not change, so W is equal to 0 here. And if that's the case, then delta U is just the Q going from B to D, because W is equal to 0. So it doesn't matter its sign, okay? You add 0, subtract 0, it doesn't matter. So QBD is actually equal to 22 joules. So we have answered this part of the process. We know how much heat is in that section. It's 22 joules. It's a matter of finding the other heat now. It's a matter of finding QAD. Remember the first question, to find the overall heat from ADB on that process itself, going from A to D to B, okay? And that we found it to be 45 joules. 22 of these joules are from B to D. So if we remember the calculation that we did, and we found 45 joules, what is the 45 joules? Here, it's from A, D, B. From A, D, and B, we found 45 joules. Here, 22 joules already. So here, we must have 23 joules added in this section. That is because that's how much heat we added altogether. We added 45 joules, and we just found 30 minus 8, which turned out to be 22 joules of heat, pure heat only, because there is no W in this section. It's an isochoric process. So W is 0. So everything we added in terms of the energy, because this point sits at 30 joules above this point, that is how we calculate delta UB, delta UAB. And now we calculated delta this much work, this much, because this is 8 and this is 0. So this must be 30 minus 8, which is just 22 joules in U. And that is Q. Why? Because delta U is 0. So we're left with 45, because its entire section is 45. We calculated it earlier to be 45 joules. So we're left with this section being 45 minus 22, which is 23 joules. So we can say QAD is simply the entire heat in this process, ADB. I have to use this exact energy in this process. This amount of heat, because heat depends on the path. And this is the path we took to that to go through. So QDB, and this is 45 earlier, and this is 22 just now. So this whole thing is 23 joules. I think this problem, we did it, everything. There is no other questions. Makes sense? These two problems, these three problems?
Yeah, makes sense.
Okay, very good. So the more you practice these things, the more you're going to be in good shape. before I get into the lab, let me tell you where we stand. Typically, these problems are missing something. They're missing the entropies, because all of this question so far is finding the work, finding the heat, finding the work, the energy. But the entropy also is another quantity of interest to us that typically we ask about it in any of these processes also, how much change in the entropy of the system, okay? So typically the question that is missing, that's why this type of problems are not really exam problems unless complemented, unless completed. And usually we ask about the change in the entropy. How much did the entropy go up or down, and so on and so forth. So that's the question that we typically ask about these problems. So if you see something similar to problem 39, for example, for during an exam, it's going to include this question, okay? Because that's a natural extension for these problems. That's one thing. The other thing also, if you look at the process, for example, on this problem, ADB, I'm sorry, ADBA. So if you look at this problem in here, A to D to B back to A, this is a cycle. Because the starting point is the ending point, albeit we go through the points D and B in between. Or if we go through A, C, B, A, that is actually another process, okay? So this is actually another cycle, I'm sorry. So this is another cycle. If you're careful enough and you look at the paths of these two problems, A, D, B, A is counterclockwise. So if you look at it, this one, this is counterclockwise. So this is like an AC unit or refrigerator, okay? If I look at the problem, the other path though, A, C, B, A, this is actually clockwise. This is like an engine, okay? Another extension of this problem, because of these patterns, if I am interested in any of these cycles, I'm going to be asking questions that relates to how well this either AC unit does or how well this engine does. In here, I will be interested in the efficiency. How efficient is this engine is, okay? In here, I will be interested in the, oh, I forgot the word right now, blanked on it. The coefficient of performance, that's what it is. The coefficient of performance of this heat pump, okay? So this is the typical questions. Now, come exam time, you're going to be seeing stuff like this one. So these problems that we've been doing need to be completed, and the way to complete them is to add the question of the entropy and the other question of how well they are doing, whether it's an AC unit or whether it's a heat pump or whether it's an engine. So in this case, how well it's doing answers the question is how efficient it is if it's an engine, or what is its coefficient of performance if it's a heat pump, okay? So this is just to basically put you in perspective so that you guys see where these problems stand in terms of the overall picture, okay? This is the questions that you're going to be asked to do, okay? The entropy, I know we're not getting into it yet, by definition is not really that hard. It's dq over t, that's all, okay? And then we're going to be doing all kinds of integrals using this one, and that is from Tuesday of next week. So this is, and it turns out to be also a state variable too. Okay. Any questions about these problems? No? If we don't have any questions, we're going to jump into the lab now. So week 3, We pull the lab, here it is. Share. A lab is due February 12th, which is coming soon, okay? So this labs are, we have to get them done before the actual exam. The exam is going to be toward the end of the month, the 4th week of February. So that is when the exam is going to be due. So we're going to get a lot of this materials in. These labs sometimes are very helpful and instrumental toward the exams too. They're actually very good preparation for the exam. So we really need to get these things going. You will see the instructions for the lab, which are in here, which hopefully you download them. And the rubric is in here and how this is going to be graded. Let me make sure I have the lab open, and I will share with you the screen for the lab. Stop sharing. Share.
I have a quick
file.
question.
Yes.
Oh, I know that like in order to like open all those like the lab and all that, we have to like get like the discussion and the quiz done first. I was wondering if there's like a way you can just unlock everything for the week, so we don't have to wait to like get one item out of the way so we can get to the lab. I don't know if that's too much.
Can you repeat the first part? I missed it.
So like on the modules, in order to access like lab 3, we have to finish the discussion and the quiz first. So like I was wondering if there's
Yeah, it's going to change down the road. At this point, I want you to really get into the habit of going sequentially about it.
okay.
But
I see.
automatically, actually down the road, this thing is going to be changed, okay? Changes on its own, so that there is no. So right now for week 3, there is a prerequisite, which is week 2. And it says complete all items. If you look at week 4 does not really have a prerequisite, okay? And it does not have to be completed in sequence, so you can jump ahead if you want to. I hope this is the question that you're asking, is it?
Yeah. Thank you.
So it's going to be that way because actually there is a reason. Week 4, actually, you have to do it anyway to do the exam. So unless you're planning not to do the exam, that's fine. So this is really to get you in the habit of how to do things. And then after that, it's going to be loosened automatically. So this is what's built in already in Canvas. Okay. This is in purpose, actually. Okay. So let me close. No, I don't want to close this. And let me go into the PDF file. And let me share the PDF file. Share button. Okay. So here is the lab instructions for this one. Don't forget your name in here. As you go about this, usually it's a good idea not to start the objective right away. I know probably you have a very good idea of how the lab look like. So you might be tempted to start with it, but leave it for a second or two until you complete everything. However, don't forget it. You're going to lose 3 valuable points in here if you don't do this. Okay. The lab talks about the adiabatic process. That's what the adiabatic gas law. Okay. So the adiabatic gas law can be written as PV to the power gamma equal to a constant, which is called K1 in here. This expression can be turned into different forms where gamma is all of these expressions in here. For a polyatomic gas, it's roughly about 1.3. Okay, because it depends really on quantum mechanical processes involved. For a diatomic gas, it's 1.4. For a monoatomic gas, we've been using to be 1.67. Okay. Now it says since air is comprised mainly of nitrogen and oxygen, and this lab will assume gamma to be 1.4. However, more accurate calculation will involve a weighted average for all of its components. I know N2 is 1.4, and you know oxygen is 1.4, but there are other elements. It has water vapor in it, it has carbon dioxide in it, and those are for sure polyatomic gases. So it's going to be slightly less than this number or around this, slightly different off of this number, okay? So if a monoatomic gas is compressed adiabatically to half its initial volume by what factor does the pressure increase? Repeat the same calculation for a diatomic gas, namely gamma changes. So the first case, you're going to use gamma equal to 1.67. The second case, you're going to use gamma to be 1.4. In the third case, you're going to use roughly gamma equal to 1.3, okay? Which undergoes the greatest change in pressure. Okay, here is what it's asking. Look at this formula. P is equal to P, if you wish, P final times V final to the power gamma is equal to P initial times V initial to the power gamma. That's what this expression is saying, okay? But what they are saying in here in this question is half of its volume. So the final volume is half of the initial volume. So VF is 1/2 of VI. So we plug in here P final times V initial over 2 to the power gamma equals to P initial times V initial to the power gamma. Obviously, V initial to the power gamma and V initial to the power gamma from both sides cancel, and you will be left with P over 2 to the power gamma equals to P final, or P initial, I'm sorry, times nothing, because V initial to the power gamma canceled. You guys understand what I'm talking about or not?
Could you repeat it one more time, please?
Okay, let's draw it on a Can I get the pen? No, I can't get the pen. Let me stop sharing and let me move this to the other screen, because if I do it on the screen, it's not going to work. The pen works only on one screen for some reason. Okay. Oh, I could use the notes there. That's fine. Share the same file. Okay, so this is what the question is asking. You see the PDF file or not?
Yes, we can.
Okay, so here is what it says in here. Okay, I can't, I have to add notes. Oh man, I hate this PDF, the new PDF thing in here. What is the notes in it? No, I don't want text box. Insert text box. Yeah, let's do it a text box. Okay, so here is what I'm saying. P times V, and this is final, okay? So I'm going to put the F next to it, times VF to the power gamma. I'm going to put G instead of gamma, okay? Is equal to P initial times V initial to the power gamma also. Here is the thing. According to this expression, V final is equal to V initial over 2. That's half of the other one. So if I plug into this expression, it becomes an algebraic expression that basically reads the following. P final, or P final, times V final. V final is V initial over 2 to the power gamma. So it's going to be V initial to the power gamma divided by 2 to the power gamma equals to, according to this law, P initial times V initial to the power gamma. Now, V initial in the last expression to the power gamma and V initial to the power gamma, they cancel from both sides. So we'll end up with PF equals 2 when I move 2 to the other side to the power gamma. So it's going to be 2 to the power gamma times P initial. So whatever that P initial is going to increase by a factor of 2 to the power gamma. In other words, this implies that basically PF over PI is equal to 2 to the power gamma. So the pressure will increase by 2 to the power gamma, where gamma is 1.67 for diatomic gas, 1.4 for 1.67 for monoatomic gas, 1.4 for a diatomic gas, and roughly about 1.3 for a monoatomic gas. So all you're doing is finding the power of 1 to the power 5/3 and 1 to the power 1.4 and 1 to the power 1.3. Okay, and find where the highest increase in pressure is going to be. So that's the question. Does this question make sense to you guys?
Yes, now it does.
Okay, so it's really using that expression and subbing the values of gamma in here and telling me which one has the highest increase. Okay, now it's defining these processes. Isothermal process, that's where the temperature doesn't change. Isobaric process, that's where the pressure does not increase. Isochoric process, that's the pressure that does not see any changes in volume. It's called an isometric process because the length, basically, which is the meters, don't change. But that's the volume, really. Length times length times length, or sometimes called an isovolumetric process. Isentropic process, which is called an adiabatic process, is a process where the entropy doesn't change. Okay, this is the one that we talked about. This is the whole lab. It's about this process, really. And then there is an isenthalpic process where the enthalpy does not change. So what in the world is the enthalpy? The enthalpy is another form of energy that basically is defined as the internal energy of the system plus PV. So it's U plus PV becomes the enthalpy H. And the enthalpy H has to do with the heat. This is usually typically is important for chemical reactions and processes that involve changes in N, okay? So it's a much easier way to talk instead of Q heat to talk about the enthalpy, number one. Number two is the enthalpy is actually a state variable also. So it's not unlike the heat, which depends on the path, depending on the process. Now this one does not. So the enthalpy actually also is just like as good as the energy, it's just as good as the entropy and everything else. There is another function that typically you're going to encounter if you delve yourself into thermodynamics a lot, and that is the Gibbs free energy. And the Gibbs free energy is defined in terms of actually the enthalpy itself and the actual, what is it? I forgot the other name in here. I think that's probably the internal, in one of the two things anyway, okay? It's a step in between these two things. This is not going to be relevant for all of us in here for this class, the enthalpy, so it's really not something to be worried too much about it. But if you're going to do chemistry or biology or other things, you might encounter it with vigorous things, okay? But it's a good thing to know in here, that's all, okay? But these are typical processes that we talk about. We discovered the 4 of them, all 4. This one is not part of the class. PV equal to NKBT or nRT, depending on which way you write it, where N is the number of moles in the case of R, or N is the number of the actual molecules in the case of KB. That's all. Where KB and R are just related to one another using the Avogadro's number Na. Where KB is Boltzmann constants in this case. For sometimes, especially in chemistry, they use per unit mole. So we make the distinction for KB to be per unit actually molecule. But that's just really a number. So that's why in the proper units, in the references, it's always joules per Kelvin. There is no number in there, okay? So if you multiply KB by temperature, you're gonna get energy, you're gonna get a joule. Okay, during an adiabatic compression, okay? We compress it adiabatically. Does the temperature increase, decrease, or stay the same? If there is a change in temperature, how can this be happen if there is absorption or expulsion of heat? There is no expulsion. So that's what the adiabatic process in here is. Adiabatic process means, can I add another one of those things? Oh, there is a free pen in here. Okay, that's fine. So Q is equal to 0. Why it's not writing in here? Oh no, I can do that. So let's add another text in here and that's it. Be done with it. So Q is equal to 0. That's what we're saying. So there is no adding heat, there is no removing heat in this process. Yet the question is asking during an adiabatic compression. Okay. That means the pressure goes up. Is there an increase in temperature or decrease in temperature? Compression also, you can think of it as the volume shrinking. Remember, T V to the power gamma minus 1 is constant, meaning the initial value of the temperature and the initial volume of the volume are satisfied with this condition with their related parts in their final state, V F to the power gamma minus 1. Okay, obviously, if the final volume is less than the initial volume, and if you do these ratios in here, you find that the final temperature will be higher than the initial temperature. Just follow the algebra, that's all, okay? In other words, this expression says that TF over TI is equal to the ratio of the volumes VI over VF to the power gamma minus 1. Okay, remember VI is less than VF. I'm sorry, said the other way around. VI is more than VF, so the ratio is less than 1, but you're increasing it to a power that is less than 1. So we're going to look at this expression, for example, for a monoatomic gas, how much it is, for a diatomic gas, how much it is, and for a polyatomic gas, how much it is. And you tell me, does the temperature increase or decrease? And of course, it's going to change. It's not going to be the same, albeit Q is 0. So although Q is 0, but we're compressing the gas, so we're working on it. So we're adding energy in the form of work to the gas. So the internal energy must increase, therefore the temperature must go up. So that's the explanation, and that's the answer to the question. Make sense so far?
Yeah.
Okay. So the last question in here is that we use this TV to the power gamma minus 1 extensively, and it's relating K1 and K2 via this constant and KB. And in the PT diagram, it looks like in this convoluted form, which is 1 over gamma minus 1. And this gives you another constant K3. And the question is to show these expressions in here, that's all. Using PV equal to nRT, or PV equal to NKBT, I should say, because we're using NKB, not NR, okay, not the little NR. So what you're saying in here is, go back to this expression. What is it? PV to the power gamma equals to K1. And remove P using this expression. What is it? NKBT. Must have missed it here, equation 2. So you're going to replace P with NKBT over V into this expression. And now all of a sudden, you're going to have T and V by themselves. Of course, V to become to the power gamma minus 1, and K will be divided by NKB. Now, you go back to the same expression, PV to the power gamma equals to K1. Okay, and use equation 2 to eliminate V off of it. So V is NKBT over P, and sub in the expression of V here. So it's going to be P times NKBT to the power gamma over P to the power gamma, and that is equal to K1, and you move the things around, and you're going to find a PT in this expression, and that the constant now, the new constant K3 will be all of this expression in here. So that's basically what's asking you is to do this thing, okay? Now for the lab. The lab, I give you a link in here from Wikipedia that gives you what the lab is. So you go in there if you want to read about this one and how to determine the gamma basically for this different gases is you can go back into there and read more about it. And for the animation, it's straightforward, really. So basically what this formula is going to give you at the end is going to give you omega, the angular frequency, okay? And it tells you what the value of the pressure is. It tells you what the cross-section of the ball is, the area, tells you what the mass is, tells you what the volume is. And from here, you can use it to find what gamma is. You can use this expression to find what gamma is. Gamma is going to be clearly omega squared over times mv over pa squared, okay? So you go back into the lab and you fill the data in here, verify that this expression given above for both frequency and angular oscillations, namely check the units in here. Gamma has no units. P is actually measured in Pascal, which is force divided by an area. And you have an area squared. So it's going to be force times area. So it's going to be kilogram meter over second squared times meter squared. That's what the area is. Divided by a kilogram. That's what the mass is. And you have a volume in here, which is meter cubed. So cancel all of the units, take the square root, and you should find radians in second or 1/2. This should be in second. Okay, just the inverse of this expression, that's all. Okay, just to check the units in here. Using the above expression for omega and t, find the expression of gamma. So we're going to solve this equation for gamma and calculate the angular frequency for pressure that is 1 atmosphere or 101,300 Pascal and a volume of 8 liters, which is 0.08 cubic meters, and a ball of 1.6 centimeters. So the volume is 4 pi over 3 times this radius, which is 1.6 divided by 2, which is 0.8 centimeters. Convert the centimeters to meters to find the volume in cubic meters, remember? And a mass of 10 grams. So you have M, which is 10 grams. And the gas is a monoatomic gas, diatomic gas, and triatomic gas. So basically, gamma is equal to 1.67. Gamma is equal to, in this expression, 1.4, and gamma is equal to 1.3, okay? 1.33, okay, respectively. And you're going to find the calculations in here. Don't forget the units. This step does not require units because it's just proving things, but this step requires units, okay? And this table in here is going to come from the simulation. So we're going to go through the simulation quickly, and this value will come from the simulation also, because you're going to average this value in here. You're going to average this value in here. You're going to average this value in here, and you're going to take the numbers from there and check the linear dependency over the volume, because you're going to change the volume and the omega squared will change on you, okay? And you're going to graph the data and answer this question. Does it meet the requirement, and is the slope equivalent to that? And now the conclusion. So let me go back to how to get the data for our lab. It's this link, which is a GeoGebra link. So I'm going to click on it. Once it opens, I'm going to move it to the other screen. And I'm going to stop sharing the PDF. I'm going to share with you the animation. So right now it's triatomic gas. So I'm going to move it to monoatomic gas. The volume is 8.2 liters. So I'm going to change at some point the volume. Okay. Please restrict it between 8 and 13 liters. Okay. And the atmospheric pressure between 990 millibars to about 1,025 millibars. This is actually in millibars also, okay? 1,000 millibars is an atmospheric pressure. So that's another way of measuring the pressure. There are at least 4 common ways of measuring the pressure. The SI unit is Pascal, ATM, atmospheric pressure, used extensively, and also the bars, millibars, not really a bar, and usually 1,000 millibars is actually an ATM. And then what is the other unit? Is the mercury, basically, level, 67 mercuries, or so that's what the weatherman actually uses. Okay, and the amplitude of oscillations in here. So basically what's going on, you take ball in here, and under normal pressure, its own weight basically sits on the gas in here, so it's going to be in equilibrium. If you move it, there will be depression underneath of it, so the pressure from the top will push it down. And because of the mass, is going to continue down and oscillate now. The pressure will increase underneath, so it's going to push it up against the atmospheric pressure. When it moves up, the atmospheric pressure will move it down. And this is what this Richardson experiment is, Richard's experiment is. So that's basically how to find this. And the relation between omega, the angular frequency, or the period with gamma is how to find gamma. This is one of the earliest experiments that was done to find the value of gamma. So now I'm going to go, it's going to give me omega. So this is what omega for this number is. So this is trial 1, okay? If I have to change the volume, I'm going to change the volume, okay? And it gave me a different value for omega, okay? And so on and so forth. So guys, you understand basically what you're doing. If I don't have to change the volume, if I stay with the same volume, okay, and repeat this experiment, it's roughly going to give me the same value, which I'm going to average. This is for the first table, okay? So the first table, all I'm doing in here is repeating this experiment, okay, for a monoatomic gas several times, I think 5 or 6 times, until I get an average value for my experiment, okay? Till I get an average value for my experiment. Then I change the gas from monoatomic to a diatomic gas and do the same experiment in here. Obviously, the value of omega will change, okay? And I'm going to plug it in there, and so on and so forth. So if I change the gas to for the third column, for the triatomic gas, I'm going to should find a different value for omega, okay? And so on and so forth, okay? Do you guys understand what you're doing for this lab?
Yes.
Okay, so it's really straightforward. If you want to read more of that theory and the derivation for that omega, please do so. I have it actually included in the PDF file also. And if you have difficulty with it, please let me know. Remember, the first part all you have to do is just change the type of gas to find the different values of omega and repeat it several times until you get enough data to find your averages. And the second step is actually changing the volume and finding that dependency of omega on the volume and finding the slope to be consistent with those gammas. That's basically in a nutshell your lab. Sounds good?
Sounds good.
Okay, so what I'm going to do is I'm going to stop the recording first, then turn off my video and audio. And if you guys want to hang around, that's fine. If you want to leave, that's fine too. But don't forget you have a due date that is coming soon for this lab and the other labs and everything else. So I'm going to stop the recording completely. If you have any questions while basically my video or audio off, please just speak up and give me about half a minute or so, and I will come in here. That is if you hang around. If you leave, that's fine too. Thank
Sounds
you.
good. Thank you, DJ.
Problem.